Hello everyone, welcome to chapter 12. I hope you have had a great week, and we are going to actually talk about further abstraction techniques. Some of the things that we will cover, we will talk about abstract classes, interfaces, how the abstract classes interact with interfaces, and as well as multiple inheritance and how interfaces act with the inheritance. We only have two more chapters to cover. We are only going to go up to chapter 14, and so I just want to make sure that you understand this chapter. This is also important. It's kind of continuation of the inheritance. We might not be able to finish completely chapter 14, but we try to do some part of it, and then we only have a couple of more assignments. I just want to remind everybody that if you haven't turned in an assignment, you can turn it in, but you will lose some marks, but it's better than getting a 0, because as you see, every week you have an assignment. So by the end of this course, you would have had like 14 assignments to turn in. So I just want to make sure that everybody understands that, and we will only have the final exam. I'm actually trying to do a quiz, one small quiz, maybe on week 13, and so that you know the burden is not going to be too much on the final exam. So at least I will give you another quiz that maybe you can just focus on few chapters. I'm just going to mention it to you what chapter you're going to focus on, and for next week we will have another quiz in week 13. Okay, so let's start with this topic today. Today we are going to actually talk about simulation in this chapter, and we are going to actually look at the benefits of simulation. Maybe some of you are familiar with it, but for those of you who are not, let me just explain something very briefly. Basically, computers are used to simulate real systems. The system could include to model like a traffic in a city, maybe a weather forecast, also simulate the spread of infection, also simulate the stock market, and environmental changes maybe, and other aspects that they can use simulation. When we are creating a computer simulation, we try to model the behavior of the subsets of a real world in a software model. Every simulation is basically necessary to basically simplify the real thing. So rather, because normally if you want to implement something, it might be costly, it might be too dangerous and things like that. So you're going to use a simulation model, which will kind of simulate that environment, but it's not going to cost that much, and it's not going to affect a lot of different things. So the more the detail would increase, the complexity of the model and the requirements for both the computing power and as well as the programming time will increase as well. One of the simulation that's very well known that maybe many of you would know is weather forecasting. Basically, climate models in a weather simulation, they have been improved by adding more detail over the last few decades. As a result, you see that people can forecast more accurate. And you see that, if they're predicting that it's going to rain, probably it's going to rain 90% of the time. But again, it's not going to be like 100% accurate. The benefit of simulation is that we can undertake the experiment that we couldn't do with the real thing because we have no control over the real thing, or because it's too costly or dangerous, or basically irreversible in case of a disaster. So an example of the use of environmental simulation is to try to predict the effect of human activity on natural habitat. For example, consider a case of national park, which contains a lot of endangered species. So they are having a proposal to be the freeway throughout this basically forest. and basically completely separating the half. The supporters of the freeway claim that splitting the park in half will lead to little actual loss and make no difference to the animal. But the environmentalists, they don't believe in that. So how can we basically tell whether likely to be, what would be the effect without building that freeway? Well, as I said, simulation could be one option. In that case, you're going to look at it's going to be less costly, it's going to be safer, cheaper, and quicker. So, and in that way, you can use a simulation model. So normally we are trying to simulate the effect in order to make a well-informed decision, and this is very popular nowadays. In this chapter, we are actually going to look at the foxes and rabbits simulation. Basically, this is kind of like uses the freeway example as I described it before. It involves tracking population of foxes and rabbits within that closed area. This is basically is known as predator-prey simulation. And this type of simulation they are often being used to model a variation in population sizes that can result from a predator species feeding on a prey species. So basically there's often a delicate balance between a species. A lot of prey means a lot of food, and a lot of food means higher predator numbers. So the more predator, they eat more prey, and less prey means they eat less food. However, we know that basically loss of part of the food chain can have dramatic effect on the survival of other parts. And so basically, this is basically in the project model that we have. And same as before, we are going to start with a version of application that kind of works very well at the user's points of view, but from the internal view as a programmer is not really a good object-oriented design and implementation. We are going to go use different versions to develop several improved versions of it, and we are going to actually introduce the new abstraction technique in this chapter. So you can open the project and you can see the main classes in here are simulator, fox, rabbit. And the fox and rabbit class, they provide simple model of behavior of a predator and prey. In this implementation, we are not trying to provide an accurate biological model of real foxes and rabbits. We are just trying to show the principles of typical predator-prey simulation. Another important class here is simulator, which is responsible for creating the initial state of simulation, controlling it, and then executing it. Basically, the simulator holds collection of foxes and rabbits, and it repeatedly gives those animals an opportunity to live through the entire life cycle. At each step, each fox and each rabbit is then allowed to actually carry out the action and basically or their behavior. After each step is done, the newest current state of field is displayed on the screen. So as we said, the main classes are fox, rabbit, and simulators. The other classes that you can see in that diagram is basically field, location. Basically, the field represents the two-dimensional enclosed field. Basically, the field is composed of a fixed number of locations, which can be arranged into rows and columns. And one animal can occupy a single location in that field. Location represents also two-dimensional position, within the field and specify as well by row and column value. Then we have the simulator, basically simulator view, field stats, and the counter classes. They provide basically the graphical display of the simulation, and the display shows an image of field and encounter for each species, the number of rabbits and foxes. So this is basically the graphical display of foxes and rabbits simulation. So you can see in the visualization what we talk about, the location and all that. And another class was counter, which stores a current count of one type of animal to help with the counting. So that counter is counting one animal plus. Now let's look at the detailed implementation of rabbit, fox, and simulator class, which are the important classes of this this project. The rabbit class, you can see the source code in here, or you can go to your project and double click on it and you can see the source code. The rabbit class basically contains a number of class variables that define the configuration settings, and they are all common to all rabbits. So some of the fields that is kind of important in here, also we need to know the rabbit's age, basically whether the rabbit is alive or dead. And also we need to know the location, the position, basically rabbit's position. And we need to know if the field is occupied or not. That field is occupied, we can position the color of the rabbit both, yellow and blue. It either has to be empty or it has to be rabbit or fox. The next thing, we are going to look at the rabbit's behavior, basically. One of the methods that we are going to, like a rabbit can basically run, that's one of the methods, that's one of the behavior. So, which in turn uses the give birth and increment age method and implements the rabbit's movement. So basically, age increment at each simulation step, and a rabbit could die at this point, basically. Rabbits that are old enough might breed at each step. New rabbit could be born at this point. So that's how this rabbit behavior is basically functioning here. So both the movement and the breeding behaviors, they have random components. So, as I said, the direction in which the rabbit moves is actually randomly chosen, and the breeding also occurs randomly, and it's controlled by the class variable breeding probability. So we also said that basically, so for the simplification purposes, rabbits, they don't have different genders. In fact, all of them are female in this project. But if we want to actually, it would be very interesting if we have a simulation that runs for both male and female, because that's in reality, that's how it is. Also, for simplification, we have the same rabbit could breed at every step. And again, that could be different in real situation. And also, all rabbits die at the same age. And as you know, that's not true. But for the simplicity of this simulation, that's what we are assuming. So let's look at the other classes. A fox. As we said, fox also is very similar to the rabbit class. The only thing that is different, if you can see here, the age is different, if they can live or not, the position, the field that they occupy. There's something that's different is basically the food level. The fox food level, which is increased by eating rabbits. Why we didn't have that in rabbit? Because rabbit, they don't eat fox. Fox eats rabbit. So that's a new field that we have in this class. Let's look at fox behavior. So the method that we have here in rabbit, we had run. In here we have hunt method. Foxes also same as rabbit, they also age and breed, and they become hungry. So they hunt for food in adjacent locations. So let's look at configuration of foxes. So similar simplification to rabbits, we are going to have hunting and eating could be modeled in different ways. Should food level be additive, and is a hungry fox more or less likely to hunt? These are, we have to see if these simplifications are basically acceptable. Let's look at the simulator class setup. The simulator class has basically three components: the setup in the constructor, the populate method, which each animal is given a random starting age. So that's the random, we talked about the randomization. And then the simulate one-step method, it iterates over separate population of foxes and rabbits. Then two field objects are being used, field and update field. So in the update step, the iteration operator, it runs over and over till the next rabbit. And for the fox, it's the same thing. The iterator is basically kind of running over and over until the next fox. So for room for improvement, we're going to actually go and look at the project and see the version, and then we're going to discuss more about how to do the room for improvement. So if we can go back to our project and open the project. So we can go and open our project. So we have the Fox and Rabbit project version 1, as you can see in here. Okay, we are going to compile this now. And we are just gonna look at one of these classes. The source code, Fox. You can see here we have three utility: Java util, list util, iterator, and random. We need those three. And in here we have basically public class Fox. Anything that you see in caps, they are basically static variables. Static variables are fixed. They don't get changed. I mean they call constant variable. They are static. They are fixed. And in here we have the breeding age as 15, a maximum age that they can live is 150. We have the breeding probability, and we have the maximum litter size, which is 2. And the rabbit food value is 9. So basically this is a shared random number generated to control the breeding. So after 9 newborn rabbits, then something they can eat, the fox can eat the rabbit. And then we have down here we have these fields in here, which we have described before. And the rest of the program, there is explanation. I'm not going to go into the details. Basically, it's very simple. You can just see, basically, just follow these. So in here, this is what the fox does most of the time. It hunts the rabbit. In the process, it might breed, die of hunger, or die of age. So this is basically showing you this description. So if alive, give birth, new foxes. Also new location, you find food. If the new location is empty, no food found, try to move for a free location. And then if, again, see if it is possible to move. If it's not, no. Otherwise, set dead, die, it's overcrowding. So the next one, it checks whether the fox is alive. So we have the is alive here, and if it's alive, then you return alive. So this is the is alive method here. Then you have the get location method here for returning the location. And in here, place the fox at the new location in the given field. So you have the set location here. And then increase the age. You will increment the age. So this could result in next fox dead. If the age greater than maximum age, then it's die. So the maximum age is 150. So in here, make this fox more hungry. This could result in fox dead. So if the food level is decreasing, then again, if they don't find the food, then again die. In here, look for rabbits adjacent to the current location. Only first live rabbit is eaten where food was found, or nor if it wasn't. So this is another thing that you can see in here. And then the last one is basically kind of checking whether or not the fox is to give birth. At this step, new birds will mate into 3 adjacent locations. And then here you have the generate a number representing the number of birds if it can breed. Again, remember these are constant variables that we have defined here. Anything that's in caps. So return age, breeding age, if it can breed. And then indicate that the fox is no longer alive. It is removed from the field. If it's dead, then it's going to be removed from the field. So for the rabbit, it's the same thing. You can go through the program. So I'm just going to go through the simulator and basically create a new simulator here. And as you can see, this graph is popping up. The yellow one is showing the rabbit, and then the blue one is showing the population of fox. As you can see, there are 214 fox here, 782 rabbits. So we're just going to actually, with long simulators, you see it can actually go up. So you can see that it's increasing, decreasing, increasing, decreasing, all that. So we can go, oh, I have to stop this. So this time we're going to go one step at a time. See, I'm in the step 2. You can see I can go step 3. You can see the number of fox and rabbit. Rabbits are increasing. You can go one more step. Step 4. 156 to 1100. Step 5. Again, you can see how it's spreading. Or I can just put a number here. Let's see till 1000 how it will look. So it's gonna run up to step 1000. And that's how you can see how it's spreading around. So this is how it's actually working. Another way that you can look is under fox and rabbit graphs. You can see in here, so the fox and rabbit, it could be animal, superclass, subclass, and then we have a simulator view, which also is going to have grid view, where also will have a graphic view. So let's compile this first. Everything is working. New simulator. So as you can see here, we have both the graphic view and the grid view. So let me just step through it. So I'm gonna do one step. As you can see, it's increasing. See, 2 step, 3 step, 4 step, 5 step. You can see that this is the graph is going. So I'm gonna put until like 100, 1000. You can see the simulator is moving, the graph is moving. So it's going through 1,000 steps. As you can see, it goes up and down based on this, and it's a stop, 1,005. So this is how you can see the both graphic view and the grid view.